Yeah. Okay. So this is like a second talk on Dieudonne theory. So I wanted to start by sort of trying to recall a little bit of what happened last time. And in particular, I think towards the end, we were sketching this construction of an extension of O-Chris with the CW. And actually, Bailinson emailed me, and then he explained to me like something simpler that one can say. So I just also wanted to begin with that. So we call that sketch to prove that so the key point in this proof was this construction of an extension. Was the construction and this was some sheaf that we had denoted by the symbol. So this construction is actually much simpler to explain in the case where, say, if we work with the direct limit of this WNs taken over the Birchable maps. So this is something we were calling the unipotent Ovid vectors. So what we have to do is that for every, so let's say A, an ideal, and gamma be a divide power structure. So we'll construct an extension this form. And so this is the thing that we want to construct. So this is what we want. So I think this we had explained yesterday. So not just last time.
Excuse me, should it be CW underlined or just plain CW?
Yeah, sorry. So I think if we write the underline, then we could just write A and the ideal and gamma. So in this case, we can just write it as like CW. Thank you. Yeah. So we always have this exact sequence. And in coordinates, one can write this like this. So the idea is to construct a section of this map V. And so
I'm going to be here for.
We will construct a section. So this will be the section S that we will construct. And it will be a section to the map V. So once we have such a section, we can set so the goal for us really is to construct a section here. And think yesterday, sorry, last time when I was explaining, so in Butler, Breen, and Messing, this section is constructed by directly writing down the formula and then checking that it's additive. But so actually in this picture, there are certain other identifications that one can make, which makes it very easy to see what this section should be. Okay, so to construct a section, so here actually we can make a very general observation that since I has divided powers, so there is a isomorphism of abelian groups as follows. And this works for similarly for the truncated ones as well, which I'm not going to write. So it's actually quite easy to sort of explicitly write it down. So what we can do is, so in general, we have the Witt polynomials, but in the presence of divided powers, we can actually suitably try to divide those Witt polynomials. So let me write them down explicitly. So these expressions under quotes actually make sense because I has divided powers. And the way that this map is defined, this will be additive, and one sort of clearly sees that this will have to be a bijection as well because of these terms like A1 and A2. So this is clearly a bijection. And also additive. So if we make this kind of identifications, then we can simplify this CWU as an abelian group and just write it as and then the coordinates on this side, maybe I'll denote by different letter. So all but finitely many of them have to be 0. So we can also try to understand how the map denoted by V on CWU would behave under these identifications. So this map would be simply given by shifting again. And so this is something one can check just by this formula. You can try to sort of add a shift by 0 here, and then you'd see that like the expression just basically shifts. So now to define a section, we can just try to pass to these other coordinates written as in terms of SSWs. So here so this map can simply be constructed by adding a 0 here. And then by definition, this is clearly additive. And this also gives a section to the map that we had. Let's start. So I mean, after this one can also kind of pass to CWU and see that it would exactly match up with the formula that I had written down in the previous talk, which was given by Butler, Breen, and Missing. So let's see what's happening here. So I guess more concretely, what you see is that, say, if we take some expression like this, then this will be mapped to W0, W1, Wn minus 2, and then 0 in the end. So in order to find this, all one really has to do is kind of solve here to make the last coordinate 0. And so this is all we did. So this expression here is just there to make sure that I can make the last coordinate 0 by using the very explicit formulas that we have written down. And so at the level of CWU, one can write the section as and so this is the formula that I think we have written down in the last talk. But under these identifications, the fact that that map is additive and I think the additivity is clear, and it also kind of explains how to find this section. Okay. So with this, I think I will start with the plan for this talk. So at first, we'll go over the definition of p-divisible groups and define the classical Dieudonne module in the case of p-divisible groups. And then after that, we will begin by discussing what happens over more and more general base rings. And then towards the end, we'll pass to the stacky approach. Okay. So let me start by writing down these definitions. So let P be a prime and h greater than 0 be an integer. So p-divisible group G of height h over scheme S the direct system Gn of finite flat group schemes over S such that each Gn is p to the n torsion of order p to the n h, and the transition maps Gn to Gn plus 1 induces an isomorphism Gn onto p to the n torsion in Gn plus 1. So some examples of this definition is of p divisible group. So let's take A be an abelian scheme. So then we can define a p-divisible group associated to A in the following manner. So take the p to the n torsion for each n. So this is a p-divisible group of height equals 2 times the dimension of A. So for now, let us suppose that K is a perfect field. G divisible group over K. So using what we did in the last talk, we can define the Dieudonne module. Define the Dieudonne module of G as inverse limit over the Dieudonne module of each of these finite flat group schemes Gn. So then sort of main theorem here is that functor G to Mg is an anti-equivalence between, so side we have p-divisible groups over K, and then on the other side have the category of finite free K modules equipped with some Frobenius semilinear map F, such that so in this case, this last condition here is actually just there to ensure that we can also define a map V such that FV and VF is equal to P. And given the condition you have, and also using the fact that D is finite free, just this condition would allow us to construct such a map, which we actually suppress in this case. So in this case, rank of Mg would simply be the height of G.
But in this case, it is equivalent to require there to be a V, right? Or
yeah, exactly. It's equivalent. And so going back, so we started today by saying that last time we discussed that there's kind of a way to use a certain X group inside the crystalline site, which also recovers the Dieudonne module. And so today we will see that this definition involving the X group can actually be generalized to make certain constructions when we're not necessarily walking over a base that's a perfect field, but like a completely general base scheme S of characteristic P. So, okay. So let's go G be a p-divisible group over S. So S is now just a general scheme. Characteristic P. So then definition is below when messing. So in this case, we can make the following construction. So you can take the Shiffy X group inside the crystalline site, defined in this manner. And what we prove about this construction is that, so in this setup,
Just a moment. So here, are you working with a big crystalline site or the small? What kind of crystalline site do you consider?
right? So we should work with the big crystalline site of S.
Yes. And as before, this is a crystalline site over ZP. So you allow thinkings which are not in characteristic P.
Right, exactly. Yeah. So in this setup, Mg is a locally free crystal of rank H. H is the height of G on O-crystal modules. So this defines a functor from the category of p-divisible groups over S to what we'll be calling Dieudonne crystals over S, which are locally free. So in this case, Dieudonne crystal would mean that this would just mean that we have a locally free crystal equipped with certain semilinear maps F and V such that FV equals PF is equal to P. And in our context, this extra data of being a Dieudonne crystal is just induced from the existing maps Frobenius and the Verschuborn, which are both defined on the p-divisible group G. So keeping the case over when the base is a perfect field in mind, which is what we stated here. So now, since we have this functor M, one can, in general, try to study when is this functor M going to be fully faithful. So when is M, so some question one can study, when is M fully faithful? So we'll not really get into the details of this, but I'll just try to mention some work in this direction. So
just a moment. So one question: if S is spectrum of a perfect field, then F is a p-linear operator, and V is P in 1 over P linear operator. Are there some similar words in the general definition of Dieudonne crystal?
Yeah, so I think here I didn't say this about F and V, but for F and V also one is to phrase the similarity, which will think be obtained by pulling back along the absolute Frobenius map on S.
Yes.
So sorry, I think I was suppressing that. But F and V.
But you are keeping it. But this is to be assumed because probably does it influence the property of being fully? Maybe not. Yes, fully faithful must. Yes, for fully faithfulness, this is probably doesn't matter. Okay.
Yeah. But I think maybe it's also worth pointing out that this F and V are just directly induced by like the Frobenius on G, and there we take the Frobenius G to be S linear. So we work with like the relative Frobenius on G. So that kind of keeps track of all the semi-linearity and so on. Yeah, so then like one general question one can ask is, when is M fully faithful? And some work in this direction is that, so for example, Dieudonne and Messing prove that M is fully faithful when S is a local complete intersection. Some analogous question one can ask is maybe also, when is M fully faithful up to isogeny? And in that case, this kind of results will be true slightly more generally. So let us say that S is given by spec of R, where R is a semi-perfect ring. So you're still interested in the same question, but maybe over a somewhat different kind of base. So
can you recall the definition of semi-perfect?
Excuse me, and before this, and is there a sort of, I don't know, derived Dieudonne model that would actually work, well, maybe would work in full generality? Is there a story of something like that, like derived crystalline cohomology is more reasonable when you consider not local complete intersection, but arbitrary schemes? Is there something similar for Dieudonne story?
So I think there are certain kind of work where this cohomological formalism is used, and there's also certain other kind of work where this cohomological formalism of like say crystalline cohomology is not used. So I think there are certainly like some results where you don't need the local complete intersection assumption either, and it works in like a more general setup. And I think maybe I'll mention that in a little bit as well. Yeah.
I think the brief story is that on the one hand there are deep results, on the other on the other hand the picture is incomplete, and I think it's even less complete if we work not with p-divisible groups but with finite locally free group schemes or even BTN group schemes. So my impression is that the story is not finished, but nowadays, since we have the prismatic formalism at our disposal, and especially since we have the stacky approach, things should be doable, but they are not yet done.
Yes, I guess another comment is also that I think this like stacks of p-divisible groups, they're also, I think, smooth. So it's
in the p-divisible case, they are not fine. If you consider the stack of p-divisible groups, then this is the projective limit of the stacks of BTN groups. So it's a projective limit of smooth schemes, but then it's not smooth in the literal sense. Maybe it's formally smooth or something like this, but anyway, we have to keep in mind that in this setting, our finite dimensional intuition can easily fail us.
yeah, so I think later on we will also state some results in the quasi-symptomic case. And so I think given the description of the stack of p-divisible group, you just said it could be that sometimes we can reduce to sort of working over quasi-symptomic base as well. Okay, so maybe we move on then. So say that S is Pekar, where R is a semi-perfect ring, and here by semi-perfect we mean that the Frobenius map on R is surjective. So in this case, what one can do is that, so say G is over spec R, then one can evaluate the crystal MG on this algebra called A Chris, which I'll write down the definition. It's some kind of a universal divide power thickening of R. So the way I'm writing down, I think I'm writing down everything at once, so it looks a bit complicated. And I think maybe the universal property is simpler to think about it as some universal divide power thickening. So
Yes, so I think the main point, if you wish, the definition of a crest is the following. So if R is semi-perfect, then the category of O PD thickening has well, either a final or an initial object, depending on whether you work. It's well, if you think in terms of schemes, then it has probably a final object. If you have maybe an pro object, maybe with some small caveat. If you think in terms of rings, then it has probably an initial object. Maybe these are pro objects or in objects, but anyway, you have this feature which is rather unusual if you think about usual schemes. So semi-perfect schemes are highly unusual. So, a finite dimensional scheme is not semi-perfect unless except some with some obvious exceptions. Yeah.
Right. So I guess maybe building more on like these comments. So I think this also explains why it's a good idea to kind of evaluate the crystal on a crisp, because it sort of gives me like an initial object. So in this case, the crystal will essentially be kind of determined by its value on a crisp. So which is why it's a good idea to sort of make this definition. Evaluate the crystal on a crisp. So then this is a finite projective acris R module. And we have maps So if we're walking over some semi-perfect base, then one can basically work with the category of this kind of objects. So work with category of such objects. So some finite projective acris R module equipped with two maps F and V, such that FV and VF is equal to P. And then one can study like a very similar question of when is this functor fully faithful? So when is M from the category of p-divisible groups over R to acris R modules that are locally free plus F. Okay. Maybe it's a good idea to call it M. So equipped with F, V, such that when is this fully faithful? So the assumption that R is semi-perfect in this case allows us to make the story completely algebraic again. So I think there's also quite a lot of work here to answer this kind of question. So if R is itself the form perfect ring quotiented out by some ideal given by regular sequence, then Solze and Weinstein proved that M is fully faithful. So I think more general cases appear in the work of Lang.
One in question. Do I understand correctly that if the well, it's I vaguely remember that a Chris has a derived version. So, and the reason is that a Chris is constructed as a certain PD envelope, PD how, whatever it's called. But the usual PD how introduced by Grothendieck or maybe by Berthelot using Grothendieck's ideas is too coarse. It has it's roughly speaking defined by generators and relations, and there are, in general, there are higher relations. So my understanding is that there is a kind of derived version of a Chris, and
Right. So I think under the
am I right?
Yeah, I think in this case, when R is a perfect ring quotiented by some regular sequence, then A Chris R is also the derived crystalline cohomology of R.
Yes.
But in
so-
general, if I
yes.
wanted to formulate the proper derived analog, I should just take the derived crystalline cohomology of the ring.
Yes. The assumption that R has this property of being a quotient of a perfect ring by a regular sequence is very strongly related to the fact that the A Chris you were talking about was classical rather than derived. I don't know whether passing to the derived A Chris completely resolves the problems, but at least well, I would say without some assumptions on R, the classical A Chris defined by Fontaine is a wrong object, or at least it's not quite correct.
Yes, yeah. I think I guess to add more to this, I think in this case, when I is a perfect ring quotient by a regular sequence, then this A Chris R, it also happens to be p-torsion free. And so I think maybe there are sort of two approaches one can take when trying to generalize this. One is maybe replace A Chris by like the derived version to work with derived crystalline cohomology. I don't think that's what happens in the Workout law. But what happens, I think my naive understanding is that in the case when A Chris R is not torsion free, it's not p-torsion free, I think he works with certain extra structure which also keeps track of the divided Frobenius, which is not really showing up in the kind of algebraic objects you're considering here. So I think he works with a slightly different category, which also keeps track of this divided Frobenius.
Yes, and I vaguely remember that this refinement has something to do with the notion of gauge, or maybe the notion of F gauge, and
yeah, I guess my impression is that the notion of F gauge should kind of automatically keep track of this extra divided Frobenius structures.
yes, and a good news is that okay, so so the formalism of gauges and F gauges in this setting is almost available. There are Pratt gave lectures on F gauges, and his lecture notes are available on his homepage. And as far as I understand, Bart and Lurie are writing an article on this subject.
Yeah, I guess there's also Greenwood's paper on this.
Yes, so a kind of sketch of the theory is also given. Well, something is about this, is something preliminary about this is said in an article of mine, but it's very preliminary. So, so anyway, just keep in mind that there is something on useful on Bart's web page, and moreover, we can hope that Bart and Guri will soon post an e-print about a detailed paper about.
And so I guess maybe this might also be like a reasonable point to mention that like maybe one slight advantage of using the stacky approach to sort of defining these invariances that I think all the story of having this divided Frobenius and being like having the structure of an F gauge, it's kind of automatically built into like the prismatic formalism. So I think if we are able to reconstruct the definition of the Dieudonne module as a certain prismatic cohomology group, then we automatically have all the enhancements that are built into the prismatic formalism, which I think maybe in the existing story, it seems like sometimes maybe one of them were not considered because it was not necessary, maybe because maybe the module was locally free or the base ring was p-torsion free, so certain structures were not necessary, so they were kind of suppressed. But I think in this formalism of F gauges, kind of all of them automatically exist.
Could I ask, are there any situations in which this functor is known to not be fully faithful?
Yeah, I think at least in the case of finite flat group schemes, I think there are examples. I actually haven't looked at the reference, so I apologize because I am not able to say the name of the paper, but I think it's mentioned in the paper of De Jong and Messing, and they also have the citation to that example.
Okay, thanks.
Yeah.
Sorry, follow-up question. Are there any conjectures in this area?
Sorry.
Are there any conjectures in this area on when it should be fully faithful?
Are there any conjectures in this area when it should be fully faithful? That's a good question. So I think my naive impression is that the hope should be that this should always be fully faithful, but one would need to sort of modify these categories that appear on this side. So without changing like the categories appropriately, it's not always a good question to ask if this is fully faithful. So I think the problem has the aspect to have to modify these categories as well.
Actually, some conjectures in the spirit are formulated. Well, a conjecture in the spirit is formulated in one of the e-prints I published this year, namely the first one. And this year I posted 3 e-prints. And in the first one, there is an appendix in which I give a conjectural description of the stack BT infinity. And BT infinity is another word for p-divisible groups. Of course, we don't know whether the conjecture is true, but maybe it's true with some caveats. But at least there is a precise conjecture formulated there. So there is a good candidate for the category, which is on the one hand hopefully equivalent to the category of p-divisible groups. And on the other hand, this category is described in terms of something like crystalline cohomology, in terms of some stack which is defined in the spirit of crystalline or prismatic cohomology, and moreover, the hope, at least my motivation for introducing such a description, that then one can hope for a Schmurian analogs. If you have a description in terms of, so this, the description, the conjectural description is basically in terms of vector bundles on some stack, maybe with some additional words. And then a vector bundle is the same as a principal GLN bundle. And then you can replace GLN by more general reductive groups, for instance, by E7. And this was my motivation. So anyway, there is a conjecture in this spirit in Appendix C of the first of the e-prints I published this year, and there are some reasons to believe that this conjecture is true, or maybe not far from being true. But I cannot say more.
Thank you for the comment. Okay, so maybe now let me try to sort of briefly talk about the work of Anschutz and Le Bras. So
at some point we need a break.
yeah.
So please decide about
Right. I think maybe this will take another 10-15 minutes or so. So I was thinking maybe we could take a break after this.
Very good.
Okay, thank you. Okay. So p-divisible groups over certain general mixed characteristic base, or maybe I should just say maybe p-complete base rings, studied by Anschutz and Le Bras in terms of prismatic Dieudonne theory. So I wasn't really planning to get into the details of kind of like discussing prismatic cohomology, and so I will also not explain exactly how their construction went, but I just want to mention the kind of category of algebraic objects that they were working with, which they call this filtered prismatic Dieudonne motifs. Okay, maybe let me mention before going there what kind of base rings do they work with. So they work with quasi-symptomic rings. So since I'm not giving the definition, let me just mention some features. So there are no finite type assumption in this definition of quasi-symptomic, and anything that's smooth or filtered colimit of smooth algebras, they're automatically quasi-symptomic, and anything that's symptomic is also an example of a quasi-symptomic ring. So in this case, by some descent techniques, one can focus on certain class of quasi-symptomic rings which are called quasi-regular semi-perfect orbit. So roughly speaking, one way to think about this is that there are quotients of perfectoid rings by certain regular sequences. So in short, sometimes they're also called QRSP, just. Okay, so let R be a QRSP algebra. So in this case, one can associate a prism which is the prismatic cohomology of R. So if we were to work in characteristic P, then under this situation, this prism R would agree with Acris. So maybe let me just write that this actually generalizes. Setup in characteristic P. So this prism, by definition, they're equipped with a map that's called a Frobenius map. So using the Frobenius, in this case, one can make this definition. So this is the set of all elements such that Frobenius is divisible by the ideal. So this is called the first piece of the Nygaard filtration. Definition of a filtered prismatic Dieudonne module. It's a collection following data of a locally free prism R module M prism submodule fill M and a Frobenius linear map M such that. So there are two conditions that this data is supposed to satisfy. So okay, so this is the definition of a filtered prismatic Dieudonne module.
Just a moment. So the word filter here refers to a very short filtration. Yes, you have M, and inside it you have fill M, and maybe that's it. Yes.
Yeah, exactly.
Maybe you also have P. Well, at least this is what I see.
Yeah.
What is mentioned explicitly. Second is that this situation when you have this, so this is sometimes this maybe you actually this type of structure is implicit, at least in the situation of Dieudonne models corresponding to p-divisible groups over perfect fields. So as you said, in this situation, we consider a finitely generated free module over the width vectors, equipped with operators f and v, such that fv equals p and vf equals p. Or if you wish, you can say that you have f with a certain property. But then you can consider the operation fv equals p can be also rewritten as follows. So v inverse equals f divided by p. Then, so this v inverse is, however, defined not everywhere. It's defined only on a certain submodule. And this submodule where this v inverse is defined is probably, I think this is your fill M.
Yeah, exactly. Yeah, right. So,
and at some point, probably soon, Kazimir Kotari will give a talk about the notion, Thomas Zink's notion of display. And in this talk, you will see precisely this construction. Thomas Zink suggested to, instead of thinking about V, work with, instead of working with V, work with the inverse, which is a partially defined operator with the property that under this operator is defined, it is equal to F divided by P. And here, but we are in a mixed characteristics setting, and here we, instead of P, we write I, where I probably refers to a certain prism. Am I right?
yeah, right. So I guess maybe one comment about like what you said, that here we work with a very short filtration where we essentially only consider the first piece of the Nygaard filtration. So I think from the perspective of the stacky approach, it would be that we are only kind of remembering the first Nygaard piece in the prismatic cohomology of BG. But I think if we wanted, we could also remember the whole structure of the Nygaard filtration. Just that in this case, I think the higher pieces of the Nygaard filtration are kind of determined by the first one and powers of P. So I think it should also be possible to view this whole structure of a filter Dieudonne module as like with the structure of an F gauge, where we probably remember all the data of the Nygaard filtrations and so on. But in this case, not all of them are necessary, and the first one determines all of them.
Yeah. So as far as I understand, the reason why the Nygaard filtration, or at least its relevant part, is very short, is that the Hodge filtration on the first cohomology of an abelian variety is also very short.
Right. Yeah. I guess both Hodge and conjugate would be quite short, and
Yes.
that there would be a way to determine the Nygaard from those two. Okay. So now I'll just state the main result of Anschutz and Le Bras in this setup. So the category of p-divisible groups over R. So R is QSP, quasi-regular semi-perfectoid, as before. So is anti-equivalent to filtered prismatic Dieudonne module over R. And so I'm not really describing the construction in detail, but so like their construction is given by a very similar X1 group in the quasi-symptomic topos of R. So construction uses a X1 group similar to crystalline Dieudonne theory. So just, I guess, one small comment is that I think in the current version of their paper, Anschutz and Le Bras, they have translated their definition into what they call an admissible prismatic Dieudonne module. So they are not really talking about this film, which is the piece that appears in the Nygaard filtration, but they have a different way of encoding the same data. And so I think that part of the story is more similar to the notion of, I guess, Broil-Kissenfalk's module, which are used in the classification of p-divisible groups over perfectoid rings. But the one that I was like describing here, which was in an earlier version of their paper, this filtered prismatic Dieudonne module, I think this is more similar to the work of Lau, which uses this theory of windows, and so there they have a filtration as well as a divided Frobenius. And at least in characteristic P, I think the work of Lau works quite generally in terms of these windows and the divided Frobenius and keeping track of the filtration and so on. So that was kind of the reason to make this choice of mentioning the filtered prismatic Dieudonne module. And the second reason is that I think this structure can also be seen as an F gauge.
So I'm not sure I understand all the words, and at least I encountered the word window before, but there are many people who so people here are not supposed to know what a window over a frame is.
Yeah, I don't think we will need it.
Yeah, of course, but
Sorry.
just a moment. So some of your words, I don't understand some of your words, and probably so the audience has the right not to understand some of your words. But I want to understand something basic. Are you saying that you give kind of description of what Anschutz and Le Bras did? Are you literally following their paper or not? Or maybe the paper has several versions, and in this case, maybe you follow one of the versions, but not the other. Can you just briefly say?
Yeah, okay. Yeah, so I think this appears like as a remark in the current version of the paper, but I think this
in the final, in the first, I didn't see.
I think in the final version of the paper,
In the final.
right, in the final one, I think they briefly mentioned filtered prismatic Dieudonne modules, but they work with this admissible prismatic Dieudonne ones. But I think in the version 2 of their paper, there's more emphasis on the filtered prismatic Dieudonne modules.
So you are more or less following version 2 of the paper.
Right. Yeah, so I'm following version 2 of the paper. Okay. Right. Yeah, so I guess I'm done with the first part, so we could have a break now.
Okay, now we'll take a 5 minutes break.
Can I ask a question?
Yeah, sure.
So is it, if R has characteristic P, then is this definition of the filtered prismatic crystal, like, did it exist in the literature before, kind of, or?
If R has characteristic P, the notion of filtered prismatic, I think there's notion of filtered crystalline, yeah, filtered ionic crystal, yeah, should appear in the work of law as well.
So does the theorem give like new information if R has characteristic P, or like are there rings that were not covered by Lau that are covered by this theorem now, or?
That's a good question. I think other than certain finiteness hypothesis, I think the work of law is more general in characteristic P, but I could be wrong. So yeah, at least in that work, there's no like quasi-symptomicness kind of assumption.
I see, thanks.
I had a question as well. Does this recover the notion of Broad-Kissel modules?
Does this recover the notion of Broad-Kissel modules? Yes, yeah. Yeah. I mean, if you're interested in the case of OC, then we should apply to the perfectoid algebra OC, and then this prism R in that case would be what's called ANth, and then if we apply it in that setup, we would get the notion of Broad-Kissel modules.
Thank you.
Can we continue?
Yeah, sure. Okay, yeah, so let's continue. So this is the last part of the two talks, and so I think this will be on this stacky approach. So so I think like things should be somewhat easier now in this part of the talk. So somehow here, I think the goal is that, so what one sees is that the Dieudonne module of a p-divisible group has many properties and which are very similar to cohomology of let's say algebraic varieties. So I didn't really get a chance to mention like more along this line, so I guess now I could just say some of them very briefly. So I think it also appears in this book of Butler, Breen, and Messing that the Dieudonne module of sort of any p-divisible group can be equipped with a very specific filtration that's called the Hodge filtration. And in some case, say if the p-divisible group is like defining the appropriate setup, there's a way to kind of recover the Dieudonne module of the special fiber from some Gallo action on the Tate module of certain generic fiber. So some of these are properties that one sees in the cohomology of algebraic varieties. So what we will do in this part is we will give a geometric construction of Dieudonne modules. So this will be in terms of this classifying stack. So if G is a finite group scheme, so we don't really need the assumption finite. No. So if G is a group scheme, one can look at BG, which is the classifying stack of G. And if G is a p-divisible group, one can also define so one just needs to take this direct limit in the suitable category of stacks. So now sort of the main result here stated in the case of a perfect field. So that K be a perfect field. Then Dieudonne module of okay. G, let's say a finite group scheme, and rank is a power of P. The Dieudonne module is naturally isomorphic to the second crystalline cohomology of BG. So let me try to give a very brief sketch of the proof. So what we'll show is that there's a natural isomorphism between this X group in the crystalline site with H2 crisp BG. So the proof I'm explaining, it actually really depends on the work of Butler, Breen, and Messing, because they proof that this is the same as the Dieudonne module. I think in the last talk, we discussed some possibility of trying to avoid that, but the proof I'm explaining right now just uses the work of Butler, Payne, and Lessing to prove this. So in this case, so let me just make some small remarks before actually discussing the proof. So usually there's like a technique for computing these X groups, and it uses this Brindelian resolution. So typically, one computes this kind of X groups by using the Brindelian resolution. So what that says is that
Just a moment. Do we really need so the linear resolution is something something not quite obvious, but do you really need it if you are interested only as in X1 as opposed to higher X groups?
yeah, exactly. Yeah. I think in any case for this proof, we don't need it. So I was just like explaining that in general, the Brindelian resolution is quite complicated, but for our purposes, one, it doesn't really help, and two, we don't also need it. So, sorry.
Okay, so another question is as follows. So let's recall elementary homological algebra. So suppose we work not with sheaves on some huge site, but just with usual abelian groups. Suppose you have abelian groups G and A. Then on the one hand, you can consider the group X1 from G to A. And this group classifies extensions of G by A in the category abelian extensions of G by A. On the other hand, we have H2 of G with coefficients in A, which is the same as H2 of the classifying space of G with coefficients A. And this group classifies all extensions of G by A, not necessarily abelian ones. So in this situation, the group is XG, X1 from G to A is a subgroup of H2 of G with coefficients in A. And I hope that at least as far as the so you wrote two isomorphisms, and the one on the right hopefully comes from this simple observation. Maybe not an isomorphism, but at least an embedding should come from this observation, but I'm not sure, of course. So
no, yes, I completely agree. Yeah, so I think the existence of the map and the fact that it's an injection, it should come from basically trying to say the same words inside the crystalline site. And I think the way we'll do it, it'll not be that different from, I think, the story you explained. So yes, actually, maybe it's a good idea to explain like the discrete case as well for just actual groups and so on. Okay, yeah, so let me just try to finish this remark earlier. So I was just trying to say that typically one often computes this X group by trying to resolve G by certain free abelian groups on G. So actually that approach works well when G is an abelian scheme, But in the case of finite flat group scheme, it doesn't really help in proving this kind of result. So, but instead we'll just use like much more simple-minded thoughts. Okay, so let me try to explain this then. So you have xg comma a. So G and A are both abelian groups. And then we always have a map to singular cohomology of G with coefficients in A. And this map is always an injection because this somehow classifies the cocycles that are symmetric, and in the other side you have all cocycles. And this is not always an isomorphism. So this is injective, but it's not always an isomorphism. So let's make maybe some simplified, like more simpler cases. Let's replace this A just by Z. And so in this situation, I think we have a exact sequence. So like we can understand the next term as well. So this formula is called is what's called the universal coefficient theorem. So here again, I guess I'm doing singular homology. So now if we further make the assumption that if G is finite, so then H2BG singular homology will be torsion. And therefore the Hom group must be 0. So if G is finite, we see that X1 G comma Z is just isomorphic to the singular cohomology of BG. So the way we'll approach this is basically kind of trying to obtain very similar kind of results by walking in the crystalline side. Yeah, so this part actually is quite common. So let's see how sort of we're going to make this work in the crystalline side. Okay, so let's say now we finally enter more into the proof. So the goal is to understand R gamma prism BG. So this can be computed by descent along point 2 BG. And the fact that it can be computed like this, it uses the fact that this map is a symptomic map. And just means that any finite group scheme over this perfect field K is going to be some local complete intersection. And you're also using the crystalline cohomology satisfies this kind of symptomic descent. And I think this is a result of Fontaine and Messing. So we can compute it like that. And what that would say is that can be computed by explicit kind of formula like this. And so this is just obtained by writing down the check now for this map. so far we haven't really been using the crystalline site, but we will do that in the next step. So all of these groups here can
Sorry,
now
what
be.
is meant by the limit?
So this is some diagram indexed by this simplex category, and so I think we are taking like the limit in the, I guess, in the category of it in the infinity category of chain complexes, or category of Z modules. But you can also just try to write down some like bicomplex and take the total complex, something like that. So there are also kind of concrete ways of saying this.
I think another notation for projective limit with respect to the category of delta is tot, and
Right.
tot stands for totalization.
Totalization, yeah. So the limit kind of description is somewhat helpful for us, as we'll see now. So the terms above can be rewritten as follows. So here I'm just using what we kind of gave as a definition. The crystalline cohomology of X is just defined as the free abelian group. So in the next step, we just take this limit inside.
Yeah, so far you have been doing abstract nonsense, so to say. So, there was no, it seems to me that so far you didn't use any concrete features of the situation.
Yeah, I don't think any concrete feature was used other than the fact that like a finite group scheme is a complete intersection. Or perfect. Yeah, everything else was just completely formal. And so let me just rewrite this in this manner. So this is kind of just like a notation. Okay. So this actually gives some complex on the crystalline site, which we can basically kind of naively think of as homology of BG. So now we get two spectral sequences. The first one is this X group. And if we try to make this spectral sequence a bit more explicit by trying to understand what happens when we try to study the induced filtration on H2, we actually obtain a setup very similar to the universal coefficient theorem that we were sort of discussing in the discrete case. So let's say we also get another spectral sequence. Let me write this down, which is also useful for making certain computations. So now one can use the above E2 spectral sequence. And also we can make some computations. For example, like the low degree, like singular homology of BG can be like directly computed. So this, for example, is G, and then this one. Again, these are true for any general abelian group object in a. So now one needs a, let's say, a small argument using the E2 spectral sequence. Which would show, which would give an isomorphism. So one still needs to understand like some.
Sorry, what's this H-2 say on the right-hand side?
I guess I didn't follow the question. Oh, sorry. You mean like the sign here? So it's G wedge G, wedge 2G, yeah, over Z integers. Right. Yeah, so I think this was the part that I was saying in the last talk, is that one can actually first try to prove this isomorphism, which is like quite formal and needs some small vanishings. And then one could try to compute second crystalline cohomology of BG sort of directly by maybe using the de Rham-Witt complex, and then try to reprove the comparison to the classical case in this manner, at least in the case when the group is unipotent. So you can just work with the unipotent coed vectors. Okay, yeah, so I think that's more or less the proof. And
so is there something in the proof which is not general nonsense?
I think it's just this vanishings that one needs to get to prove the injectivity has to be a surjectivity, but so
vanishing of what?
Oh yeah, sorry. So I guess say if we're working in the p-divisible case, G is p-divisible, then one needs to prove that, say, Hom G where G in O-cris is 0, for example, in the crystalline side.
Okay, this
is not very bad either, because it's enough to prove that the Schiffi-Hom is 0. And then this is something that one needs to prove, that the Schiffi-Hom is 0.
Yes, and actually this at least to some extent, this is similar to something very elementary. So what's the difference between, suppose you have, let's temporarily forget about sheaves, sites, and so on, and suppose you just have abelian groups G and A. And so what's the difference between X1 from G to A and X2 and H2 from G to A? X1 classifies abelian extensions of G by A. H2 of G with coefficients in A classifies all extensions of G by A. Now, if you have an arbitrary extension of G by A, then what is the abstraction for yes, and let me recall that when we are talking about H2, we equip A with the trivial action of G. So in other words, the extensions of G by A we are considering are central extensions. So if we have a central extension of an abelian group G by A, then what could prevent this central extension to be abelian? Well, we have for any central extension of G by an abelian by A, we have the commutator map, which is a map from G wedge G to A. So if we are able to prove that there are no non-zero homomorphisms from G wedge G to A, then we are done. So this is something elementary. And my hope is that you're doing something similar, but in the situation when G and A are sheaves on some sides.
Right. I think it's trying to tell the same story in the general topos. And then in the end, sometimes one needs some specific features to get the vanishings.
Yes. And so the main point is to show this vanishings.
Yeah. Yeah.
And do you want to tell us something about how you check this vanishing? Or maybe...
Yeah, so it's actually not difficult. So I think it's a little bit tricky in the crystalline side, but it's actually easier in the prismatic situation when you're working with p-divisible groups. So say if G is p-divisible and we are in the prismatic setup, then form G, so in the prismatic setup, this is kind of replaced by O-pris, which is, let's call it maybe the prismatic structure sheaf, and everything happens in a certain topos called the quasi-symptomic topos. So one important feature here is that this O-pris, this is derived p-complete. And so if G is p-divisible, so if G is p-divisible, then actually any map from something p-divisible to something p-complete, it has to be 0. Because I think maybe like very roughly speaking, if I have an element which is p-divisible, then this map will send it to something that's kind of divisible by arbitrary high powers of p, and by p-completeness, any such thing has to be 0. So in the prismatic setup, it's fairly easy to say, and also G is p-divisible here. If G like is a finite group scheme, and we're working in the crystalline side, which then it's sort of a little bit difficult to make the argument directly. So I think in that setup, it uses some other kind of reductions, which might not be maybe very good to mention now, but
okay.
But in this setup, it's very simple. It's just because of G being p-divisible and O-pris being derived p-complete. So this will be 0.
Sorry, why don't we use the E1 spectral sequence?
You can use the E1 spectral sequence too, and it's good for certain other kind of computations. Like say if you wanted to calculate the crystalline cohomology of BG, where G is an abelian variety. So there, this spectral sequence is very useful. But in general, I think, for what we wanted to prove, I think the E2 spectral sequence seems more reasonable because you directly have one term which exactly looks like the X1 group. So it's just more direct, or like, yeah, I think it kind of looks like it'll be more helpful to try to use the E2 one. But you can also use the E1 spectral sequence for certain other cases. So I guess maybe then I'll mention as a remark is that if A is an abelian scheme, so similar arguments, but one has to take care of the vanishings as well. Would say that this is H2 Chris BA, and then so you can use the E2, sorry, you can use the E1 spectral sequence, as you said, to prove that this is H1 sub A. So maybe you get a slightly different proof of this isomorphism than what appears in Barthelot-Breen and Messing, where I think they resolve A by free abelian groups on A. Okay, so for completeness, maybe let me also mention how this works to compare with this filtered prismatic Dieudonne module. So in mixed characteristic, okay, let me just say over QRSP base. For QRSP algebra R, so one similarly takes prismatic cohomology of BG, and this is isomorphic to the one that Anschutz and Le Bras defines for G, and the fill one is obtained by taking the first piece. Sorry, I think here it's just called fill, there's no one, but so this gives the fill one, and it's also compatible with the Frobenius on both sides. And you also get some divided Frobenius map, which comes from the general formalism of divided Frobenius and prismatic cohomology. Okay. And so actually this divided Frobenius is also kind of useful in writing down like the Tate module of G very concretely. So maybe this is an example. So using the divided Frobenius map, one gets an exact sequence which kind of directly computes the Tate module of G. And maybe as a second and perhaps slightly more classical example, let me mention this one. So let A be an abelian variety. So, and one has the following isomorphism. Let's say I assume this to be over some perfect field K, so that we are just really doing this classical Dieudonne theory. Yes, I think this was first proven in this paper of Oda, which is called the first cohomology and Dieudonne molecules. So let me sort of try and explain an alternate way to kind of get this isomorphism. So we know that H2 Chris is isomorphic to the Dieudonne module. And we also know that this is p-torsion. So we have an exact sequence as follows. So we take sorry. That's what we'll get, but go slowly. So this just comes from the Derham crystalline comparison theorem. And in our situation, one can prove that, sorry, this G should have been AP. So in our situation, one can prove that this H1 Chris of BG for any finite group scheme of rank P has to be 0. So then what we get is an isomorphism that the H2 Chris can simply be rewritten as H1 Derham of the classifying stack. And so now we have an exact sequence where this is just a multiplication by P. So this gives a map A to the classifying stack of AP. So now we can apply H1 Derham to this, and we get a map which is something one has to check, but let me just write, which induces. So somehow I think it allows one to kind of write down this maps as maps being induced from some geometric maps. Okay, I think that's more or less all I had planned. So maybe I'll stop now. Thank you.
Let us thank the speaker. Just other questions or comments?
I had a question. So where in the proof of this comparison of the Dieudonne module with the H2 Chris, where did we use the fact that the base was a perfect field?
Yeah, that's a good question. I mean, I think sometimes you'd still need a little more vanishings than I explicitly mentioned. So I think the examples using this extensions of group cohomology that I think Drinfeld was mentioning. So in the singular cohomology, there's one like vanishing that's always true is that the point has no higher cohomology. And those things are not necessarily true for, say, crystalline cohomology. So one needs to maybe walk over a perfect ring to say that the higher crystalline cohomology vanishes. So we don't exactly need a field, but we still need some assumptions for getting these vanishings.
So it would work over any perfect ring of characteristic P?
Yeah, I think this should work over any perfect ring of characteristic P.
Thanks.
Are there other questions or comments? I have an organizational question. So it's a question to Kazimir. Would you be ready to speak on Monday?
Yeah. Sure.
So my understanding is that the question to Shubhodip, my understanding is that you finished your talk, correct?
Yeah, right.
Yes. So then the conclusion is that the next meeting is on Monday, November the 6th, I presume. And Kazimir will give a talk on displays, which it is something which I skipped in my talk. In my last talk, I used displays as a black box, and hopefully Kazimir's talk will allow us to understand better Aikelau's talks, which will be given towards the end of November. And I hope that Kazimir will send an announcement of the title. So Kazimir, please send an announcement of your talk with the title and abstract to the send it to all at math, and on the other hand to the mailing list that I gave you with all people outside of the University of Chicago. And as usual, I hope that the so my understanding is that the recording will be posted on YouTube, and a link to the recording and the PDF file with the notes of today's talk will be posted at the seminar website. Let us thank the speaker again.
Thank you.
Thank you.